under kinetics, what did we say? We said we're interested in determining the rate of the reaction. So we're trying to study how fast a reaction gets to do what? To progress. That's what we said. I'm sure we're able to remember. So rates of what? Reactions. Not only rates of reactions, we also said under chemical kinetics, we are also interested in what we call reaction mechanisms. How basically does a reaction occur? Okay. So all these things were talked about, all these things were covered, all the tutorials are there. In case you want to have a basic introduction, you can just check out the links and you'll be able to follow up. Okay. So now, the basic idea is this. We said in a case where you have A and B as your reactants, and then you have C and D as your products. What you want to consider is the fact that these are going to have what we call the stoichiometric coefficients, which I'm representing using small letters. So the rate of this reaction can therefore be determined using any reactant or any product. Okay. So for example, in terms of A as our reactant, it is going to be -1 over A, and then I'll say the change in concentration of A over the change in time. So this is able to give us the rate of the reaction. Now, why do we put a negative? So when you have started with 2 molar concentration of the reactant, or any concentration of the reactant, you expect that as the reaction progresses, you expect the reactants to do what? The concentration of the reactant to reduce. So if you've started with 2 molar concentration, for example, you expect that after a short period of time, or any period of time, that concentration is supposed to reduce. So let's say it reduces to 1.5 molar concentration after 10 seconds. How would you determine the rate of the reaction? So you just want to substitute. You look at the value of A. Let's say there was a 2 there as a stoichiometric coefficient. We would have -1 over 2. And then the change in concentration would be our final, which is 1.5. Then initially we had the 2, of course divided by the time taken for that, so 10 seconds. So of course on top we can see that we have concentration, molar concentration, right? So the units are basically going to be molar per second. And then you realize that in the brackets they are going to have a -0.5, which basically explains why we are adding a negative to the formula of the reactants. Of course, this doesn't apply when we are dealing with the products. In terms of the products, what we get to say is it's going to be 1 over C, for example, in respect to C. The rate is going to be 1 over C, change in concentration of C over the change in time. So here it's positive because we expect initially, let's say this reaction was starting from, there were no initial products. We just started from like the reactants. We would expect that at the start, we just add no concentration of the product. So after a certain period of time, we expect the concentration to go higher. So the final one is going to be greater than the initial one. So the basic idea is every time you are asked to determine the rate of a reaction, make sure that your answer is a positive. Okay, that's very important for us to understand. I hope we are on the same page. So we're subtracting because our formula tells us to say it's change in the concentration of A. So change in concentration means what you have after a certain period of time, subtract what was available initially, so that is the change. So it's like if you are moving from 2 to 4, the change is what? A 2. If you're moving from 2 to 6, the change is a 4. How are you getting the change? You're subtracting the final minus the initial, where you're coming from. Does that make sense? But what? Yeah, I still want to hear what you want to say. Still. The final minus the initial. Yes. Yes. Who would want to answer that question? Is it a rule, or why do we subtract the final minus the initial? No one is able to answer that question. Okay. The initial and the final. Okay, let me just put it this way. So basically, if you want, you can do anything: initial minus final, final minus initial, provided you consider the modulus. If you do understand what the absolute value is in mathematics, then that's a basic idea. The answer will be the same. So all what we just want is the answer to be a positive. Okay? So in the case where I was putting it to say final minus the initial in terms of the reactance, I was putting a negative outside the derivative because I wanted the answer to be a positive. So if you want your answer to be directly positive, just you can do the opposite. No one is going to penalize you for that, provided you indicate to say it's 1 over the coefficient and then the change in the concentration over the change in time. Okay, so there's no rule to say no, it's always final minus the initial. Yeah. Why are we making it a fraction? Wow. Anyone who is able to answer that? Okay, I think you understand as we get to look at one of the questions based on that, you'll be able to see why we are basically considering that to be a fraction. Okay, for now, just get it that way. It's 1 over the fraction, the coefficient. Yeah. So that is the basic introduction of the rates of the reactions. So the other thing that we talked about is we talked about the factors that affect the rate of a chemical reaction. And the most important ones that I would want to still talk about were, the first one was what? The temperature. And then I talked about the concentration. What else did we talk about? We talked about the pressure. Of course, things like catalysts and what the surface area also gets to affect the rate of a chemical reaction. So all these factors are governed by what we call the corrosion theory. Okay, which is very important. So what did we say? What is the corrosion theory? What does it state? Anyone who is able to recall what you said? Chidema, are you able to remember? So particles must collide. That's one. And then not only should they collide, but they should collide with what? With sufficient energy for a chemical reaction to progress. So each time we're thinking about the factors that get to affect the rate of a chemical reaction, we want to think it in a way that, okay, what should we do to produce more collisions between the particles of the reactants involved? And then, of course, what should we do to also provide the energy that is enough for these reactants to, for the reaction to be initiated? Okay. So that's why if you look at the concentration, you look at the pressure, all these things are going to be, we're going to be thinking about them in a way that there are going to be more collisions. Okay. So for example, if we have 1 molar concentration of A and then 1 molar concentration of another reactant, so think of this is a container, right? And then that's what we have. And then me increasing the concentration, if I increase the concentration, meaning that we're going to have more of each of the particles, and then What do we expect? We expect that there will actually even be more interactions, which will lead to more collisions between the particles of the reactants, which will now favor the what? The rate of a chemical reaction. So that is the way you should think about all the factors. Now, when you talk about the kinetic theory on the other hand, the kinetic theory supports the idea of temperature increasing the rate of a chemical reaction. So kinetic theory of matter, which you already know, what we're trying to say is an increase in temperature will increase what? Will increase the kinetic energy of what? The particles. So particles will be moving more when the temperature is higher. And if you're moving more, what does it imply? It implies that there will be more collisions. Okay. I'm sure through through the experience that you have, you are able to tell to say, okay, I think the faster I move, the more likely that I'm going to collide with someone by on the what. Yeah. So make sure you connect all this to the kinetic theory and the collision theory. Very simple also. Are we able to understand? I hope I'm not confusing you guys. Okay. So, okay. So, when what? When the surface area is what? That didn't make sense. Okay, to make sense, of course, that is also part of the questions that we are going to look at. Okay, don't worry. So then I think I'm not talking about the electrodes since they are part of the questions that we are looking at. Reaction mechanisms are also part of the things that we're going to talk about. And then, yeah, I think we are ready to look at the questions just now. Unless if there are questions outside what I've talked about. So we'll start with this question. The question says, a study of kinetics, yes. When calculating what? So whenever they give you such a question, you just get to consider one. Just get any, and they all give you the same answer. So yeah, you can use a reactant, it can be a product, provided the information is given. Just use one. A study of the kinetics of the gas phase reaction of nickel carbonyl with phosphorus trifluoride gave the following initial rate. This is the concentration data. So we have a table that is giving us the concentration. So whenever you see the brackets here, you just know that it's concentration. And then we've been given the rate in each experiment. In experiment 1, we've been given the concentrations of the two reactants, and then we've also been given the rate. Now if you try to observe what was happening, what were these guys doing? So what you've noticed is from the start, from experiment 1 up to experiment 4, I think to the third one, just up to the third one, we've noticed that there was an increase in what? In the concentration of the reactant. And then they had to do something about it. They maintained the concentration in the third and the fourth what? Reaction. Okay, so that will help us understand whether the other reactant has got an effect on the rate or not. So in the third experiment, if you try to check the other reactants, you notice that it was 0.5 as well. And then look at the rate there. It was 4.8. Now in the second experiment, deliberately what we did is we maintained the concentration of the other reactant, which is nickel carbonyl. We maintained it, but then we had to reduce the concentration of phosphorus trifluoride. But what did you see? There was no change in what? In the rate of the chemical reaction. So what conclusion can you make from just the two, by just looking at the third and the fourth experiment there? What conclusion can you make? They can ask you sometimes to comment from a given data, so we need to understand what we are doing. Okay, so that's good. That's good. Concentration of the other one as an effect. Is that what you're saying? You're saying the other one has got an effect? So this one does not have an effect. So 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 what it means is we are saying after maintaining the concentration of nickel carbonyl, even the rate also was what? Constant, despite changing the concentration of the phosphorus trifluoride there as well. So this one has got no effect. How about the other one? How can we observe? How can we make a decision about the nickel carbonyl? What can we do? We can try to look at a part where the other guy is what? Is constant. So if you check where phosphorus trifluoride was constant, 0.25 in the first and the fourth experiment, it was constant. But there was an increase in the concentration of nickel carbonyl. And now try to observe the rate as well. The rate also, what happened? It increased. Are you able to see that? Which tells us to say, okay, well, even after making the other reactant constant, but the fact that we change the concentration of nickel, it has got an effect on what? On the rate of the reaction. That's how you make sense of the data that is given. Okay, whenever they've given you the initial rates of the reaction, and then they've given you the concentrations of the reactants. So don't think too much, guys. Let's try to be as simple as we can, and then yeah, these things are very, very simple. So we're just trying to observe how the rate of the reaction gets to occur. So now, for the people who are new and have not watched the tutorials yet, the rate law basically is just an equation that will help us rate the rate of a chemical reaction to the given reactants. Okay, so unlike just a rate, for a rate law, it just talks about the reactants. So in this case, we have that and that as our reactants. Okay, so we want to express a rate law in terms of what we have. Okay, so that's a basic idea there. So now the basic concept is each time you are trying to determine the rate, let me just write A because A and B to represent these reactants are just too big. So there are going to be powers M and N. So our idea or our goal is to find M and N for these reactants, and then we'll be able to show our rate law. Okay, so the basic step is to always try to identify where one of the reactants is constant, of which we've already done. We looked at the third and the fourth one, right? So what we said is try to express everything in terms of what you have. So from the formula that I've written, I've said R is equal to K, and then in terms of A and B, where A is denoting that and B is denoting that, right? Then these guys are raised to certain powers. And what powers are we talking about? So we're talking about powers M and N, right? So I'll start first of all by expressing the third one. So for the third one, what do we have? What we have is the rate is equal to K. I'm using this zero equation that I've come up with. For K, we don't know. For the concentration of A, it was 0.5 to the power at M. And then for our B, which is phosphorus trifluoride, it was also 0.5, the power n. Okay, divided by, so I'll divide by the other one, which is the fourth one. R is equal to K, then again it is 0.5 for our A, our nickel carbonyl, the same power m, and then this other guy is 0.25, the power n as well. So you agree with me that each time you have something that is the same, these will divide, right? Despite the powers that they have, irrespective of their powers, they'll always divide when they are of the same magnitude, right? The other basic idea is whenever you have got the same base, you can maintain the base and then subtract the powers, which will give you a 0, and then any number raised to the power 0 will give you a 1. So you can also use that. And then the rate, you can agree with me that they are also we are supposed to substitute the rate for the third one and the fourth one. And then from what you're able to see, we can't even waste time to substitute y, because these are the same, so they obviously give us a 1 on the left equal to. And then we have 0.5 being divided by 0.25. These are raised to the power what? The power n, each the power n. So what can we do? Whenever you have got the same power, you can combine the power from the rows of indices. Okay, just combine them and then raise them to the same power n. So if you get to divide there, what are you going to see? 0.25 is twice into 0.5, right? So we have a 2 to the power n. So 2 to the power n is equal to a 1. And then 2 to the power n is equal to 1 can be expressed in terms of in base 2. With a base 2, the power 0, right? So 2 to the power 0 is the same as a 1. The idea is we want to use indices to help us find the value of n. And we'll see that our n is equal to what? 0. What does that tell us? Just like we had said, we said B, which is phosphorus trifluoride, has got no effect on the rate of the chemical reaction. And so having a power of 0 means that we should not even indicate it on the retro. It's not supposed to appear. Okay. So we found the reaction order in respect to phosphorus trifluoride. This is a very important question because they usually like assessing you on this. So just make sure you've understood, and if you have not, ask now. Okay, so it seems we've all understood, and then we can try to find for the other one. Yes. Yes, sir. I'm about to get you. Hello, I'm able to get you. You have a question?
Where is the one coming from the equation?
At where is what? I didn't get your question, sir. Just to repeat.
I'm saying, where is the one coming from?
Which one? You mean the one that was on the left, where we said 1 is equal to what was on the other side?
Yes.
Okay.
Yes.
So, who understood where the 1 came from? No one is able to. Yeah.
So,
You're saying we divided 0.5 by 0.5?
that one came from? No, that one came from when dividing those rates. Since the rate were the same, so when dividing they give us 1.
Yes, thank you. So we are looking at this part because if you look at what is on the left from the equation that I had written, we said we have the rates, right? So 4.8 by 4.8 and they are the same, so they gave us a 1. That's what I said. And then I would deliberately not consider this one. of course, it's the best thing that you can do in a case where even the other guy is somehow constant. You can also do that. Just get the one where the other one is constant and then perform the calculations. But I'll try to ignore that. Let's try to take an assumption to say we didn't have a part where the other one was constant. How would we find the value of m? So we ignore the first one and the fourth one, and then we try to see what we can do. So I'll try to consider the which one am I going to consider? Okay, I'll not. Okay, I'll consider the first one and the second one because it's not constant. It's changing as well, so they are all changing. There are such questions where they give you 3 experiments and then only one was constant in the two experiments, and then the other one was never constant. So some of you were asking such questions. So how do you go about it? So what should we do? So what we'll do is this. We'll just do the same. I basically say consider the one that which is bigger and put it on top, because it will be easier for you to deal with the indices, because sometimes people get confused with indices. So using the same expression that we've come up with, our rate in terms of our reactants, I'll start with the second one. So my rate, so I'll not write the equations because I'm sure we are now used. So 1.92 times 10 to the power negative 3 equal to, so the rate is equal to K, and then what else? The concentration of our air, which is 0.2, the power at m. So I don't have enough space. I'll not show this other guy. Why? So there's no point of me showing. Why? Because we've already found the power. The power was what? The power was 0 in respect to this reactants, not so. So no matter what we are going to put, these don't have effect, right? So in other terms, if it was not a 0, I would have showed it there. Just at the end, I would have said the 0.2 to the power m multiplied by 0.25. Sorry, 0.50, since we're on the second experiment. 0.50 to the power that you found. Is it 1? Is it a 2? Is it a 0? So in terms of a 0, it will just give us a 1. So I'll just put the 1 there. And then over, I'll go to the first experiment. 9.60 times 10 to the power negative 4. And then K. And then what do we have? 0.1 to the power m. And then again, if I raise 0.25 to the power 0, it will also give me a 1. So no effect.
So how do you find that 0?
So if you just joined what? Or you've been around?
No. I've been around.
So what is the first thing that we did? I'm sure we were finding a value of n initially, right? Where we considered the part where this guy was constant. So
Okay.
yeah, we had 1 is equal to 1 was equal to what? Is it I'm even forgetting. Yeah, so I think that's what we had. So n was equal to 0. So after dividing on the left, what do you have? You have what? Is it 2? 2. So are we all getting a 2 after dividing on the left?
Yes.
And then k will of course cancel out, and then we have 0.2 being divided by 0.1, and this I've got the same power m. So 2 is equal to 2 to the power m, and then m is equal to what? 1. So we've now come up with our literal. So some of you were asking me to say, sir, do you show k in the literal? You don't show it. So you just say your rate is equal to k, and then of course don't use a and b, as I was just trying to use that to demonstrate. But I'll show that Nikon carbonyl, and then that I don't have enough space. So this is the power 1, and then that is the power 0. You can show it like that. If you want, don't even show the one with the power 0 because it has got no effect. Okay? If you want, don't show that. Just show the one that which has got a power 1. So this is what we call your retro. Any questions? And then they're asking for the rate constant. So you can now use any experiment of your choice to help you find the lateral. What are we going to do? So you just want to substitute. Okay? The rate has been given for all the experiments, so you can substitute the rate. And then, of course, this guy has got no effect, just ignore him. And then substitute the value of this guy, depending on the experiment that you've considered. So let's say I've considered my first experiment, I would use this one and the rate there. So I'll just divide the concentration into the rate. Of course, taking note of the power that I have. So to the power 1 in this case, it will have no effect. And then my rate will just be... So let me consider the first one. So we have 9.6 times 10 to the power negative 4 equal to K. So I'll just divide by what? 0.1. Of course, it is the power what? The power 1. Because of what we've calculated, not so. So if you try to divide there, what are you going to have? 9.6 by 10 to 10 to the power negative 3. The units. So we talked about two ways of finding the units. So I'm sure, what are the units in this case without calculating? This is what? What order of the reaction is this? So first order. You add the reaction orders. So 1 plus 0 is 1. So reaction order is 1. And what are the units for first order reaction? Hmm? It's the second negative? Are we all in agreement?
Yep.
Okay. We're okay then.
More per second.
So more per second. Okay, so Jordan is saying more per second. So what we'll do is this. We said we can say molar the power what? 1 minus n, and then we'll say S negative. So if you look at molar, the overall order of the reaction in this case was 1 plus 0 is what? 0, not so. So to give us 1 plus 0 is 0. It's a 1. So at 1 minus 1 will give us what? 0. So m to the power 0 and second negative. So Jordan, there's no molar per second. That's the rate, but for a constant, it's just per second. Or the other way that you can think about, if you're not able to remember the formula there, you just go to the retro where we are saying R is equal to. So I'll just consider A, but we know it is representing the nickel carbonyl, the power 1. For the rate, we know that it's always supposed to be, as you put it, molar per second. And then K, we don't know. For A, we know the units for concentration are always going to be molar. Our goal is to make K the subject. So I can divide both sides by m. And then this side to cancel, even this side to cancel. So we just have K is equal to 1 per second, which is second to the power negative 1. Okay, so that's the way you look at that. So there's another question that I like that I've already mentioned. I've said they can ask you to determine the overall order of a reaction. Of course, this question comes with just a mark. Why? Because you just look at the retro and you'll be able to tell. Okay, just add the powers of the reaction orders of the reactants. So in this case, we just add a 1 and a 0, so it's just a 1. Are there any questions? Any questions? Are we together? People are joining us for the first time. Angela, Gift, how is the class? Are we understanding, or we have some questions? Okay. So let's talk about something important as well. So integrated laterals, what did you say about them? So this can also help us to deal with some important calculations as well. So I gave you a way to remember this. I said just know that the final is equal to negative kt plus the initial. If you know that, that's cool. So that is for zero order. So we always start from zero order, and that is we're only going to be interested in the zero order, the first and the second. So the final is equal to negative kt plus the initial. So this is very simple to understand. Why? Because it tells us to say that when you're trying to find the final, all what you're trying to do is subtract something from what? The initial concentration. Because that's the way a reactant behaves. Like I gave you, I said if you're starting with 2 molar concentration, you expect that after a certain period of time, this is supposed to reduce to a certain level. Now, the reduction depends on the constant K of that reaction and the time, of course, that has passed. So, the longer it takes, the chances are it will reduce more. Okay. And the higher the value of K, the chances are also higher that it will reduce more. So you understand this K when you look at chemical equilibrium. I think we are starting next week, so it will make more sense. So that's why if they give you the information, if they give you the time, if they've given you the concentration, pay attention to what I'm saying. So if they've given you the concentration of the reactant A against time, why am I putting time in these brackets? So they've given you time, right? And then you try to plot this. Of course, you know that whenever you're trying to plot a graph, always we know that time is supposed to be where? Time is supposed to be on the x-axis. So let's say you plot a graph. You start, of course, let's say you're 0. No, of course, time is the one that can move that way, right? And then you have maybe 2 molar concentration, 0.5. So you've noticed that it's reducing, right? The concentration is reducing, implying that you've started like that, going down. So at the start, when you are at 0 seconds, the concentration was higher. Now with time, what have you noticed? It was reducing. It was reducing. So whenever it gives you a straight line, of course all the reactions are going to give you something like going down. Others may be like a slope like this. But always make sure to say it's supposed to be a straight line. When it gives you a straight line like this, just know that this is a zero direction. Are we together? You know, sometimes the way these people bring questions is they can even draw or bring a curve for you. Okay? And then they'll ask you to say, is it a first order reaction? A zero direction? So you need to make sense of every given table. Now, the same information applies to the other ones, but you don't use just the concentration. So you understand as we move. But know that that is the equation for the zero order reaction. And then for the first order, I told you to say, what should you do? I just said memorize only the first one, and then the others will be simple, yes?
Natural log.
So add the natural log to the concentrations only. Don't add it to the negative kt. We'll only add it to the concentrations. Very simple, not so? And then for this one, the same concept applies. It will also to be a straight line going down. Now, how do you differentiate it from the first one? It's going to be a straight line as well. If you plot the natural log of the concentration. So the basic idea is this one you're using the natural log of the concentration against time. The other one, you are just using the concentration. Okay. So when you're trying to test whether it's a zero order or a first order, what you'd want to start with first of all is start with a zero order where you don't use the natural log, just use the concentrations as they are given, plotted against time. Now, when you notice that it has not given you a straight line, maybe it is curved like this. What you'd want to do first of all is now introduce a natural log to all the concentration values. If it gives you a straight line down, just know that now what you have is what? A first order. Okay. And then the last one. What did we say to the last one? What do you do?
Okay, it's fractions find the multiplications only, and we change the sign from negative k to positive.
Okay, so thank you. So what we are looking at is, again, don't use the first order, use the zero order as well. So we'll now introduce a fraction. So the reciprocals of the concentrations. So 1 over the final is equal to kt plus 1 over the initial. So this one is different. Why? Because we expect that when you plot it on the graph, it's supposed to go upwards. That's why it's positive kt. I'm sure you do understand the gradient by now. The gradient, you started learning about it in grade, what, is it 10 or 8? So whenever you have a graph, I'm sure you'll be doing calculus soon in math. So of course, when something is moving like this, the gradient is positive, because I'm sure you do understand that the gradient is given as a change in y over change in x. So you're moving towards the positive and you're going up. So the value of y, the final one, is greater than the initial. Okay. So it's going to be a positive. And then when it's going this side, like the other two, the idea is if you have a 6, for example, and then you have a 4 down there, 4 minus 6 will give you a negative. So it's a negative gradient. So that can help you remember to say the second order is unique because the curve moves upward. So whenever I give you a graph with plotted 1 against 1 over the final, or 1 over the concentration, and then against time, and then it's a straight line going upwards, just know that it's a second order reaction. Okay. So now all these will help you to even find what we are calling the half-life. Of course, you can watch a video on the integrated retros for you to get how we derive the formulas for the half-life for each order. Of course, for your first order, I can demonstrate for a zero order, knowing that our final is equal to negative kt plus our initial. So the half-life, we said, is the time that it takes for the concentration to reduce to its half. So considering if you have something like, let's say, if your initial was, let's say, a 1, that's your initial. Your final is supposed to be what? 0.5, because we know you're moving, it's reducing to its half. The final is going to be the half of the initial. Now your goal is try to make time to be the subject of the formula at your half-life. So you correct the like terms, and then you have negative 0.5 is equal to minus kt. So this can divide and give us a positive, and then you can divide by k. What have I done? Okay, let me not use the values. Let me use let me use the letter to represent the concentration. I don't know what I'm thinking. Okay, so now let's say if the initial was A, what would be the final? It would be A over 2. Okay. Our part makes sense now. So if your initial is A, the final is supposed to be half of the initial. So you divide the initial by half. So A over 2 minus A is equal to negative kt. Now these are fractions. So I can multiply. Of course, you can still find the common denominator. You know that's simple mathematics. The common denominator, as you were told, is a 2. And then you have A minus 2A. is equal to minus kt. What are you able to see? You have negative a, or negative a over 2 is equal to minus kt, which will still give us a positive, and then we'll divide by k because we're interested in making time the subject. So it will disappear the other side, and then it will appear the other side, giving us the half-life time. So our half-life is therefore giving us the concentration of A over what? Over 2k. That is our formula for the half-life for a zero-order reaction. So equally, if you're able to remember the equations for all the other two, you can just use A and A over 2 to help you find the half-life equation. But it's very easy. It's very easy for you to remember. For the first order, for example, it's just a simple one, which is just natural log of 2 over k. This is the first order. It doesn't depend on the concentration. Okay. It only depends on the value of k. And then the other one, I think I've forgotten. I just have to perform the calculations. What is the half-life for the second order reaction?
1 divided by k multiplied by the initial concentration.
Okay, so it's very simple. Yeah, but for me, I was not able to remember all these equations. What I just used to do is just write the integrated equation, and then I'll just like get to put a and a over 2. I'll be able to find the half-life equation. I think we are ready. We have about 4 minutes. Let me go back to the questions and see what we can do. So now there's this interesting question that I liked. Where is it? Okay, this one. I think one of the students who was solving it, in fact, came to me for assistance on this one. The thermal decomposition of that is a first order reaction. So they've told us to say it's a first order reaction. They've given us a rate constant, of course, and then they're saying calculate how long it will take. So that is time. So we're trying to break down the question, and then they've told us first order. So the first thing that comes to mind is the equation. Natural log of the final is equal to, it's a negative slope, plus the natural log of the initial. So with time, these equations are just going to be at your fingertips. And then what else are they saying? How long will it take? So how long will it take? So now that's a question. That's very important for you to understand. How long will it take for 3/4 of initial quantity to decompose? 3/4 to decompose. So you don't have any values of the initial and the final. What are we going to do? Using the 3/4. No one. Okay, so anyone, is there anyone who has got an idea? Now we can answer it.
Yes.
Now, who is this? Okay, what's your name, madam?
Patience.
Not you. Because you're the one who asked me this question, so I already obviously you. Yeah. Anyone who, then do you have a suggestion on what you're supposed to do?
I think maybe
Yes?
it's better.
Or 100? Okay, we can try that. So if we consider 100 to be the initial, then what is going to be final?
So, 20.
Hmm?
So we're going to multiply the 100 by 3 over 4.
Which will give us what? 3/4 of 100 is what? and then which one is our initial and which one is our final?
Initial is 100. Final is 75.
Okay. I just wanted to deceive you, yeah. Okay. Not true. So 3/4 decomposed, meaning that what will remain is what? A quarter. Not so. You have 100, and then what are you told? How long will it take for 3/4 of the initial quantity to decompose? So 3/4 is decomposing. The final one is going to be what is going to remain. So 25 is what is going to remain. So subtract the decomposed part from the initial. Okay. So I don't know if this is going to work, but let's try it out. So 125. Then take note of the K value there is 2.4 times 10 to the power negative 3. That's our K value. And then I'll go back to the board. So we're saying the natural log of our final concentration is equal to minus KT, and then
Sorry, sir.
yes. Yes, sir.
I didn't get where the 100 came from.
So
The 100
we're just using it as a reference value to help us make sense out of this. We've just been given a fraction, just say 3/4. So we can come up with any value of our choice and then try to find 3/4 of it, and then try to find the initial or the final.
Okay, sir.
So for me, I like using 1 because it's simple. I'll just say 1 is my initial. So if 3/4 decompose, the final is going to give me what? 1/4. So I've got my initial and my final. Simple. So I'm trying to use the 100 if it's going to work. So natural log of 100 is equal to, sorry, the final is what? 25. And then our K value, I able to remember, I said 2 point what? 2.4 times 10 to the power negative 3 time. And then natural log of what? 100. Natural log of 100 to give you what? So before you can even perform any calculations, just use the logs to simplify your work. So natural log of, so we're going to have 25 minus natural log of 100. So when you have the same log subtracting, what can you do? Maintain the logs and then do what? Divide. Okay. Which will still take you back to what I was saying, which is what? 1/4. So it's the same. And then if you try to say 25 over 100, that is going to give you what? 1/4. And then 1/4 is the same as 0.75. So natural log of 0.75 divided by negative 2.4 times 10 to the power negative 3. Now what are you getting as your time? What are you getting? Hello? No one is able to. No one has calculated?
119.
Okay.
119.867.
So, Precious, we're getting the same answer when considering the 1 and then 1/4. So, what you're saying is your final is 1/4, and then initially you had a 1. So, natural log of 1 is what? It says 0, not so. So, you can just ignore that part. So, you notice that it has gone back to the same thing, not so. This is what we are just from calculating. So, it's the same. And then, which other question is important that I need to answer? I think you can answer the second one and the third one. So I'll emphasize again, in case you never attempted these questions, attempt this one, the second and the third one. Let me try to look at the questions. And then if you look at the first order, I think this is also the same. A certain first order chemical reaction required 120 seconds for the concentration to drop from that to that. Find the rate constant and the concentration of the reactant after 80 seconds. This is also simple. Are we able to answer it? Are we able to answer it? So
Yes, this one is straightforward.
this one is straightforward. If you look at the equation, they've given you the final, the initial, they've given you the time. What are you trying to find? You're just trying to find K, not so? So you do that. And then the concentration of the reactant after 10 seconds. So thereafter, what's going to happen is you will consider this to be your initial concentration. And then you try to find the final. Of course, you already have the value of K. And then you already have the value of time. And then the initial is 2. That's also okay.
The time which you're supposed to use is the 80.
The time that you're supposed to use. So these are some of the questions that may be ambiguous sometimes. Okay, find the rate constant and the concentration of the reactant after 80 seconds. Now, the question is after 80 seconds from where? Is it from 2 or from 1? So don't confuse things here. Just consider 2 as though you're coming from 2. Because if you try to think of it as though you're coming from 1, the one who has put the question may not be thinking that way. Okay? To make things straightforward, you can just consider 80. Okay? Alright, we're on the next question. I think this one is also straightforward. It's also first order. And then the rate constant has been given. And then the initial has been given. What is the concentration after? So you're finding the final concentration. We've already answered that one. And then now what fraction has decomposed in this time? What fraction? So what you're finding in the first part of the question is what? You're trying to find the final. And then you have the initial. So if you have the initial and the final, how do you determine how much are decomposed? So you can just subtract the final. Of course, you do understand the just like the madam was putting it. The one was asking questions like when you started. So it's just going to be the initial minus the final. The idea is you want the difference to be a positive. So initial minus final, and then divided by what? Divided by the initial. It will give you the what? The fraction. If I say the percentage, just multiply by 100. So the difference is giving you how much are decomposed, and then in respect to what was available initially. I don't know if that makes sense. What you have finally at the final point, and the difference between the final and the initial will give you how much was lost, in short. Are we together? Hello? Are you able to get me?
So can you explain why you are dividing by the initial?
You're saying what fraction? What fraction of are decomposed? What fraction? So what are decomposed in relation to what was available initially? Okay. I think the basic idea, we can do this. Let's say initially we have a 2, and then after a certain time we had 1 molar concentration. And then they ask you to say, okay, let me use a different value so that we don't get confused. So let's say we have 0.5 as a final. So how much are decomposed? You know that it's going to be the difference between 2 and 0.5, which will give you 1.5. So you know that 1.5 are decomposed. Now, out of what? Out of the total 2. So, of course, these have got a common, so it will be 3 and then 4, right? So, 3 quarters are decomposed. That's a basic interpretation. Okay. So whatever you're going to find, subtract from the initial and then divide by the initial. And then this question, I don't know, Faith, if you've been able to answer this question now, or you're still looking at it. I posted this question to the group some time back, and no one has responded. Huh? Okay, somebody who has sent the solution. Okay, I'll have to check them again. Okay, I'll check. So what are we supposed to do? Is there anything different? Or is it just the same?
There is something different.
How is it going to be different? Of course, the only difference part is what? The fact that we don't have the other concept. We just have a single reactant. So there'll be no need of you trying to find a case where it's going to be what? Where it's going to be constant. It's not so. This one I think is even easier. Not so. Because this one is just going to be straightforward. So our rate is equal to what? K in respect to what? To what? I'll use A. So I'm just trying to find the power there. I'll consider the first and the second one. So my rate is equal to K in respect to that reactance. Not so. So my rate is what for the second one, which is bigger? 4.4 times 10 to the power negative 6 is equal to K. And then the concentration on 0.2. The power at any letter of your choice divided by the first one was what? 2.2 by 10 to the power negative 6, and then K, and then 0.1 m. I think this one I can even answer it without a calculator. We can all see that. So this is going to give us a 2 is equal to, and then the other side you also have like, you can maintain 0.2 divided by 0.1. Since they have the same power, you can just give them the same power as well, right? The power at m. So 2 to the power 1 is equal to 2 to the power m. M is equal to what? 1. Are we together? So I think I've answered. For argument's sake, let me try to check the other parts. The third one, 6.6 times 10 to the power negative 6 over 4.4 times 10 to the power negative 6 is equal to, and then I can say, of course, 0.3 over 0.2 the power m. Try to divide what we have there and see what we're going to have. So just take a tip for you guys. Whenever you're trying to divide things with the same standard form, whenever you have the same power this side, just cancel these. Okay, just consider that part on both sides. So on both sides we have 1.5. So all in all, our value of m is going to be what? 1. Isn't this simple? This is like simple. Very simple. So that is our rate rho. And then the rate constant for the reaction. Just get any equation of any experiment of your choice. And then substitute the rate rho, or the initial rate, and then the concentration. And then try to make K the subject. So the fact that this is also a first order reaction, the units are going to be second negative. Wow, guys, me, I'm tired. Just one more question. I think we can answer this one. Yeah, we can answer this one. I think it's one of the students as well sent this one. I know it's Martha. Yeah, I think it's Martha who sent this question. So this question says, when C is being formed at the rate of that, Okay, I'm just tired and then. Okay, I think we can end here. So for this question, guys, what you just do is the reaction is A plus B giving you C. That's all. You're just trying to find the stoichiometric coefficients that you have. So all you do is write in terms of express them in the way that you'd write them, of course. The rate of A, the rate of the reaction in terms of A is going to be -1. Okay, let me forget about the negatives. So the rate in terms of A is going to be what? So we'll just say A over C, or A over A is equal to, let me put it this way, yeah, is equal to B over B is equal to C over C. So these are just stoichiometric coefficients. Of course, if you go to the formula, all we know is this. For example, the rate of the reaction in respect to A is -1 over A. Change in concentration of A over what? Change in time. But I'm trying to think of it in the way our sister was putting it. To say, don't, like, the basic idea is we always want to get a positive. Now, why should we subtract a bigger one from the smaller one? So, just do things any way you feel like doing them, provided you get a positive answer. So, the fact that we've been given the rate itself, we can get it and then ignore the negative and then just put A on the bottom. So what you notice is for the rate in respect to A was what? A is 0.172. So I'll say 0.172 over A is equal to, for your B, 0.258 over B. And then for your C, you have what? For your C, it was what? 0.086 over C. So what you can just do is you're trying to find the ratios of these guys. So divide by the smallest one, which in this case is this one. Yeah, so divide by the smallest, you'll be able to get some values. Yeah, so whatever you're going to get on top are the values of are the stoichiometric coefficients in respect to the reactants and the products. So we end here this evening and then see you tomorrow. We have a class tomorrow, so if we are good to go under kinetics, and then tomorrow we can review thermodynamics and electrochemistry. So I think we end here. Enjoy your evening. Make sure you rest for now. Don't just go to the books. I'm sure you're tired. So, and then you can try to review what we've talked about some other time.